So in this part we want to look at the angular speed of a charged particle moving in circular motion in a magnetic field. So we have the charged particle and it's moving in a plane that's perpendicular to the magnetic field. The magnetic field is into the page, and as we showed before, that the particle will move in a circle. And the angular speed is defined to be the rate at which the angle changes with time. So if you take the angle, the reference angle, to be 0 here, then the way that this angle changes with time is d theta by dt is called the angular speed. Now from geometry we know that the arc length of the circle S is related to the radius and the angle by S is equal to r theta. So if we write down S, the arc length, equal to r times theta, we can get theta in terms of the arc length over the radius. So we can replace theta over here in this equation. The radius is constant because the charge moves in a circular path with a constant radius, so r is a constant. So d theta by dt becomes d by dt s over r. Since r is a constant, it goes out and you get 1 over r ds by dt. Now ds by dt is just the linear speed. And so the linear speed, then we relate this way we relate the linear speed to the angular speed, and the relationship is through the radius r. So we know now that the angular speed is just the linear speed divided by r, but we know from before the previous video we found what r was, the radius. The radius was mv over qb. So if you substitute the r here to be mv over qb, you get that the angular speed is v over r, and at the same time it's qb over m.